Okay, we'll start. So we have seen few of your theorems. Okay, today hopefully we will be doing your that is maximum power transfer one. Okay, everyone knows this. Will provide lesser information on this, whereas we'll go on more on to the numerical part. Okay, so we'll just account or we'll just make a small revision on this. Okay, so we'll say that or we could say that this maximum power transfer occurs when the resistive value of the load is equal, okay, in value to that of the voltage source internal resistance, okay, allowing maximum power to be supplied. Okay, this what a very thing information what we get. Or if we see your, this is your Vs R of S. Okay, okay, this one. Okay, so in this, if we account this particular thing, okay, as a Thevenin equivalent circuit, okay, so we could consider in our this Thevenin equivalent circuit in this picture, okay, the maximum power, okay, the maximum power transfer clearly states that the maximum amount of power will be dispatched or would be dissipated, okay, in this load segment, could be dissipated in the load segment if it is equal, means this resistance, okay, this resistance would equal to the value of your Thevenin or Norton. Okay, let's take Norton resistance or Thevenin resistance source on the network. Okay, hold a second, please. Okay, fine. We'll move ahead. We'll move in a faster rate. Okay, now, so I could describe this particular segment in another format as well. If we account this as AC into CSN, let's take this as your ZS, that would be equal to your RS plus JX. Okay, and this would be your Z dot, and this would be your I flowing. Okay, so we could account this particular circuit as your Thevenin's model. Okay, this is the counter with Thevenin, where this Z will consider as a variable part where we could accountable, we could write your RL plus, let's take ZXL, it will be good. Okay, we'll make a star mark. Okay, that this is a variable. Okay, it's not a constant part, this would be variable. Now, how to find the conditions for the maximum power transfer from this source particular point to this load, from this source to this particular load. Okay, now, so from this we could see if we calculate this particular I, so your I could be written as your Vs by, that is your Zs plus Z, right? So it could be further be written as based on your this particular segment. Okay, based on this whatever it present in your circuit, it would be written as your Vs, that would be your Rs plus Jxs plus your RL plus Jxl. Okay, could be written as Vs by Rs plus RL plus Jxs plus XL, right? We could consider this particular segment. Now we know, okay, your that will be considered at power loss at that particular segment. We could write your I square ZL, okay, or you could account R square RL, okay, that would be your magnitude of I whole square ZL, or magnitude of I whole square R. Okay, you could account in any of the two segment. Okay, let's consider this particular unit only. Okay, now, so we know if we will write this, then your P would be I square RL. Okay, so if we replace this I with your Vs by Rs plus RL whole square plus XS plus XL whole square, and this would be square and will be written as RL. We will consider this as your first equation. Okay, that we'll consider this particular as a first equation. Now, to find maximum power, okay, to find P max, so your RL would be differentiated with, okay, so your it will be rho RL, your RL would be 0, where Rs is equals to RL, this particular point. And second condition is where the XL would equals to 0, which is your XL is equals to minus of X. Okay, these two conditions would be applicable in this. Okay, starting your Z part, we know that your ZL equals to RL plus JXL, and your ZL would be your RS minus JXC, right? If we consider this to particular segment, where we could also consider your ZS star would be this. Okay, so yeah, so, but we know your ZS is your RS plus CXL, whereas we get ZS star and the differentiation of this would be your RS of minus of X's, okay, which are equal. So at this particular condition only, we could account your maximum power would be stated. So we could tell that finally we could note down at three conditions. ZL would be your ZL star, okay, one segment. Your RL would be your RS, that is your second segment, and your XL would be minus of XL. Okay, so these are the three conditions. Okay, conditions for maximum power. We'll write. So condition for maximum power transfer. Okay, this is the condition for the maximum power transfer. Now, so what while doing this three, what we have noted down, or we could make a conclusion out of it, that to find, okay, your maximum power, okay, that is transferred from your source side to the load side, the impedance, your Z, okay, must be a complex conjugate of the source impedance, right? Should be the complex conjugate of the source impedance, right? This part, that your load, the load impedance should be the complex conjugate of source impedance. Okay, therefore the source, okay, the source and the load must be equal. Okay, resistive part. Okay, should have the equal resistive part. They must also uh, have your equal reactive parts. Okay, but opposite in sign direction. As these three, what we have got is the same conclusion we are getting now. Therefore, if the load is inductive and the source should be a capacitive and vice versa. Okay, this is the accountable thing. That now, so the maximum power, okay, transferred to the load is only 50% of the total power generated by the source. This is the second condition, that, or second point to be remembered in the maximum power transfer, that only 50% of the transfer, okay, to the load is to the load, only 50% of your power is being transferred from the or source, or which is being generated by the source. Okay, so this theorem is always very irrespective of nature of your source, the load impedance, okay, the nature of the voltage and current sources. Okay, so these are the point that you have to write. Now what I will provide with you a question, or we could will provide with you question. Okay, consider, let's practice this. The more we practice, will be good for this, because theory part you have already learned and you could also read in some way. Okay, this is your question. That is your 20 volt. This is 1 2 3 4 RL. Okay, this is your point A, this is your point B. So what we have to find, okay, we have to find your RL value, okay, so that the maximum power is delivered from source to the load side. Okay, this is the question. Just tell me the value of R. Just practice this. Okay, I will write this question over here. I'll write the given circuit, find the value of RL so that maximum power is transferred, okay, from source to the load. Okay, this is the question. Okay, this is your 20 volt, 1 2 3 4. This is the value, and we have to find your value of RL stated that maximum power is transferred from source to the load segment. And also, right, also calculate the maximum power. Okay, so 2 point. One is to find the value of your RL and also find the maximum power that has been transferred. So this is the question. I will provide you with a few minutes. Just tell me how to proceed and how you could do this. Then we'll see. Anyone could answer how we could proceed, or how what will be the answer of this? You have to find RL and P max. Okay, this is the question. Anyone can answer? Anyone is doing? Okay, at least tell me or help me out with the procedures. Okay, so I will draw a circuit over here. We'll proceed with this. Just tell me what will be the answer and how we could proceed. It's a very easy one. Okay, I will help you out. Okay, few things to be remembered for this whenever this kind of question is given. One is your RL would be equals to your RS. Okay, that is very important. Second one is, if we convert the any circuit in Thevenin's model, okay, it will be a very easy one to solve. Let's reduce this circuit in this particular manner. Okay, VOC or VTH, whatever you call, R equivalent or RTH, whatever you call it. This is your RL. Okay, this is the circuit. If you could convert this particular segment in this circuit, it will be a very easy one to solve. Okay, now, so if you are finding your VOC, okay, okay, for VOC, what will make it? It will be deleted from this particular source. Okay, this particular figure. We're left with this. Okay, now, well, what we'll consider this as your I1, this as your I2. We'll consider this particular segment. So how what will be the equation over here will be your I1 plus 2I2 equals to 20, where I1 would be equals to around 20 by 3 ampere, and for I2 write 3I2 plus 4I2 equals to 20, so I2 would be equals to 20 by 7 ampere. Okay, this will be what we're left with. So what will be your VOC? VOC, okay, at this particular segment where this is your I equals to 0, so this would be your VOC, right? And these two are in parallel, okay, which has been connected. So we could easily write on seeing this figure that your VOC would be your 2I1 minus of 4I2. Okay, this will the equation will get. So on substituting this value would be your 2I1 is your 20 by 3 minus 4 by 2 is your 20 by 7. Okay, so it would be your 40 by 3 minus 80 by 7. Okay, so if we could write 280 minus 240 by 7 21, that would be written as your VOC would be your 40 by 21 volts. Okay, this is your VOC part, right? Now what has been left is left with your this RL and R equivalent. Okay, so what will happen, we know if we find your R equivalent value, okay, and we know RL is equal to RS, okay, where in this particular figure this also be written as your RS, that will be equal, so we'll also get the these two value. Okay, now what we have to find, we have to find the R equivalent. Okay, so if we reduce that particular segment, we know two of are in parallel with the other two. Okay, where this would be a 1 2 and 3 4. Okay, so where R equivalent would be equals to 1 parallel 2 in series with 3 parallel 4. Okay, so whatever value we get, let's see what value we get. What will those values? Answer would be around 1 parallel 2, right? Plus 3 parallel 4. So it will be your 3 into 4 by 7, 2 by 3. I think so. This would be the, okay. So 21, 14 plus 9, 4, 36 equal to 50 by 21. This is your 50 by 21. This is the R resistance, and we know, okay, for maximum power transfer, okay, your RL would be your RS, that is equal to your R equivalent, so it will be 50 by 21 ohm. So we know RL is your 50 by 21. Okay, this data we got. Now the second question was asked to find P max. So what is your P max? P max is your I square RL, right? Now what is your I square? I square is your VOC by RS plus RL whole square, right? Then it will be RL, right? So we could write this VOC by 2 RL whole square RL, which will be written as VOC whole square by 4 RL. Okay, this RL or 1 RL will be cancelled. So this is what we left with. Okay, so we could easily calculate what is your VOC. VOC is 40 by 21. 40 by 21 whole square by 4 into RL. This is your 50 by 21. Okay, so it will be around 1600 by 21 into 21. Okay, over here will be 21 into 4 into 50, so it will be your 200. Okay, so this 2 8 21 21, so it's around 8 by 21 watt. Okay, so that is your P max is equals to 8 by 21. Okay, this is what we got. So this is how we could proceed with our questionnaire sessions. Okay, so I will provide you with one more question. We'll see if we get time. We will be doing this, or we'll do in next class, or we will ask you to do. Practice these questions. It will be help you out. Okay. This is your question. So write the value. This is your 1. This is your 10. W is T. Again, this W. Okay. This is 1. This is 1 by 4. F. This is your 1 by 4F. This is your 1 by 2 Henry. Okay, and this is your Z. A, B. Okay, this is the question. Now, what we have to find? We have to find the value of impedance. So that maximum power is transferred to it. What is the question? Yes, time is less. Okay, so this is your question. We have to find the value of this Z. Okay, this is 1 by 2 Henry. This is 1. This is 1. This is 1 by 4. This is also 1 by 4. Okay. Okay, you have to find. We'll see in next class. Okay, how we could utilize. This is your 10 sine omega t, where omega value is your 2. That's why it is written. Okay, 10 sine 2 omega. Okay, now you have to find the value of Z. Okay, it will not take much time. You could easily find what you have to find. Only you have to find your first of all, you have to find your Excel. Okay, Excel XC values. Okay, what will be the Excel XC values, and convert that particular segment in the circuit. Okay, reform the circuit, and you could utilize that particular thing. Okay, when you have to find your this part. Okay, so this would be your homework. Just do it. Just at least give a try whether it will be very convenient to do or not. I have all I have already provided you with the information. And I have also given you a hint. Okay, these values are given in this reference. What you have to do is you have to convert in your Excel and XC. Okay, and based on that you have to find Z equivalent. That will be the value of your Z. Okay, whatever the value of Z would be coming would be your Z equivalent. But the condition that you have to keep in mind that your ZL would be equal to your Z conjugate of Z source. Okay, this is for Z part. Whereas RL is your RS. For XL would be of minus of XX. Okay, if it is asking these three different domain, okay, you will find this. For RL we have done just, for ZL you have to do so. Okay, so whatever you will find the Z equivalent part, okay, using this you have to find the conjugate of this, and that your work would be done. Okay, so we are left with less than 1 minute, so we'll see in next class. I will request all to practice whatever I'm giving you. Okay, at least you will be in touch with this kind of questions. Okay, but I know a lot of questions are being untouched. Okay, and even you does not practice, it's good opportunity to practice. That's why less your theory and more of numerical. I'm hoping to get it. So you'll have different kind of numericals. Okay, then we'll see. There is another thing. Do visit your portal and give attendance whenever you will get the time. Okay.